Okay, Bismillah ar-Rahman ar-Rahim, wa salatu wa salam ala Mursaleen, Sayyidina Muhammad, wa ala alihi wa sahbihi ajma'in. Assalamu alaikum everyone. So, last lecture, okay, inshallah. So, this is the last lecture. I'll be doing the talking. Next lecture, inshallah, you'll be doing the talking, okay? So, before we start, today's lecture, inshallah, will be short, okay, and interesting, and, very little to study actually in it. We'll just wrap things together, so it's just a soft ending of the course, and then inshallah afterwards we're going to have some time if you want to discuss anything related to the project. Okay, so third lecture on the impedance control part. So today inshallah we're going to be looking at one of the points that we actually left out in the previous lectures, which is how do we design an impedance in 6D. Okay, so how can we talk about impedance for the rotation and translation at the same time. And we're going to come back to the geometric picture again. So everything we were doing is just the idea of the impedance control and how it works in just Euclidean space. Now we're going to be making it into a little bit geometric. And then we're going to talk about something different, okay, but within the same class than impedance control, something called admittance control, which is, you can imagine that is related because of the relation between impedance and admittance. Okay. So recap, the idea of interaction control is that don't think of it as a control of the pose or the wrench at the end effector separately. They are both coupled in the sense that in the end, you want to design a desired impedance behavior, a desired behavior between the wrench and the pose at the end effector. Of course, it depends on the task, but the same idea, okay, holds in general. And then this, okay, came concrete into became concrete as a control approach using by the work of Neville Hogan. 1985, and he named it impedance control. And he got this inspiration from electrical impedance, and then he talked about mechanical impedance and how the robot itself behaves as an admittance, and as how the environment itself behaves as an admittance. So the robot should behave as an impedance. Okay, so this was how the inspiration he got it from. The way actually, if you read this paper, is actually not that difficult. It's not mathematical. It's actually just conceptual. And the way he actually gets these concepts from is, from something called bond graphs, and which later something called Port-Hamiltonian theory. Okay, so actually he was thinking about it in a way that's very generic and applicable for different physical systems. We talked about the joint space dynamics. Okay, so the usual form. Okay, so we have the inertial, we have the fictional torques, or the Coriolis and the gyroscopic terms. You have the friction and the gravity, and then you have the control torques, and you have the interaction torques. Okay, so the interaction torques come from that the robot is interacting through its tip with the environment. And we said that in order to design the impedance, we would like to look at it from the task space perspective, so from the end effector. And we said that the mapping from joint space to task space and vice versa is done through this geometric Jacobian that we've seen before and we've derived earlier in topic number 3. So the Jacobian relates velocities in the joint space to velocities in the task space, while the Jacobian transpose relates the forces or wrench in the task space to torques in the joint space. Okay, so it's always this duality. And then we saw that we can take the manipulator dynamics and we can transform it into this form by just multiplying before and after by J inverse transpose. And you're going to be finding that we're going to have something that acts as the inertia of the end effector body, an apparent inertia of the end effector body at the end effector port, or at the end effector body, the apparent nonlinear friction seen from the end effector, the apparent gravitational forces seen at the end effector, or wrench in general, and you have the interaction wrench, and we have the controller. Okay, we just map it. Okay, so if the wrench is mapped to torque through the Jacobian transpose, so torque is mapped to wrench through the inverse of the Jacobian transpose. And the whole idea was if you have a desired impedance in mind, okay, and this was the point that we left last time, how do we actually look at it and how do we actually characterize Q? So Q in general, we just want it to be an error variable between the desired and the end effector frame. And Q dot will be simply the time derivative of it, and the Q double dot is the second derivative. We want to have this mass spring damper behavior, okay, between the end effector wrench, so anything that's applied at the end effector, and this variable between where okay, the virtual set point, this desired place where we want the robot to be, and the actual place of where the robot end effector is. And then we looked at different ways of how we can write the control law, and just it follows naturally from this equation. You say, okay, this is what I want the equation to be, this is what I want it to have, so okay, what should the controller be? Okay, so simply the controller, what the first is the most straightforward is simply cancel everything on the left hand side, compensate for all of the dynamics, and put whatever you want here. Okay, so if this is what we want, okay, so this is the desired behavior, put it and cancel everything else. Okay, so that's simply the easiest way of doing it, and it's more of like the feedback linearization way of doing it. Let's cancel, kill the whole dynamics, and let's just put our desired behavior. And we thought that this has some drawbacks of its own. Okay, it's not possible actually that we know all of these parameters precisely, because this includes all of the inertia, generalized inertia parameters of everybody, all of the lengths, and they have to be known perfectly and so on. So we saw a simplification, a simplified version of this, where we say, okay, let's forget about the inertia part. So let's not change the inertia of the system and simply put something that looks like that. Okay, so and this works for very slow tasks. And we said that here we're going to be canceling the friction and the gravity, so but not the inertia of the manipulator. So if you implement this controller, the person interacting with the robot will feel the actual inertia of the robot. It will not be modified. And then we saw that the simplest case was simply if we also, say that, for example, we have quasi-static interaction. So this term, if the twist is small, then twist squared will be even smaller. Then we can just neglect this term and only compensate for the gravity and put our desired spring and damping behavior. And then this controller law was very similar to what we discussed earlier, which is the PD and gravity compensation for motion control. And we said that essentially, if you look at them, they're very similar, in nature. However, they came from different ways of thinking, and extending them is also depends on how you thought of it in the first place. Okay, so they are really separate. Okay, but just even if you compare these two, you can just point out some immediate differences. Here, for example, this is a controller in the joint space, while this is simply in the task space. This uses the geometric Jacobian. This does not need any information about the geometric Jacobian. This regulates every joint to some theta desired, while this only takes the end effector and gives you so it takes you to XD. XD here represents the state of the desired where you want to go. So it's like Q is like XD minus the actual X. And this minus itself is what we never discussed so far. And the end effector behaves like a Cartesian spring and damper, while here it behaves like every joint behaves like a spring and damper. So you see, this is the spring, this is the damper at every joint, and this is the gravity compensation. This is the spring and this is the damper, at the end effector, and this is also the gravity compensation. Okay. So any questions so far? Last lecture, everything clear? Okay. Now the final question that we'll answer is that what is this equation? How do we say that this is what are the different ways to characterize this? And this will open much more doors than we're going to be answering. So you're going to have much more questions when we discuss this part today, because it depends. You can do it in so many ways. And today I'm going to just point out some ways and how they differ. And you can really do a lot of research on that. Actually, one of the projects I remember in the first list I provided to you was actually something related to this. You remember I told you that one of the projects is actually to compare different controllers for the Franca arm. No one chose that project, unfortunately. But it's actually related to this. So if you want to play around with it, we have the Franca arms, in the lab. You can come and you can test things out. And you don't need anything than MATLAB information just to hook up with the robot. So now we already saw the way of setting this desired impedance behavior when we looked at the case of the point mass. So if you remember, when we looked at the point mass, we said that Q in this scenario, the point mass lives in R3. So the state of the robot is simply given by psi. Psi here is the position of the point mass in space, and psi desired is where we want it to be, or at least the virtual set point. So, and psi d were connected by the spring and damper. And we said that the controller, the desired behavior, would be simply given by this equation, where B and K are the damping and stiffness of the virtual spring and virtual damper that we added. Interaction is the interaction force coming from between the point mass and the environment, while M here is the physical mass of the robot, which is here just a point. So in this case, you see the control. What we're actually trying to do is that we don't want to change the inertia of the point mass. Okay, so this is the same inertia it has, and we're only going to be modifying the spring and damper behavior between Q and F int, where Q here is simply psi minus psi desired. So you can see the position of the point mass and the position of so in other words, the two ends of the spring and the damper, they are defined by psi and psi desired. That's exactly what Q is. So Q actually is simply the elongation of the spring. Okay, so you can think of Q here as just the elongation of the spring, and Q dot is the derivative of that variable. Everything here was R3, so we did not face any problems here because this was the planar case. Yes.
This is the case of point mass, but you mentioned that M is the mass of the robot. Is it the mass of end effector or the complete robot?
No, I'm talking here. Our robot in this example is just the point mass. This is our
But if you have a robot, will it be a mass of end effector or the complete?
Right now. Okay, so that's the case of the robot. We also looked at something else. Yes, Samar.
Why don't you want to change the behavior of the mass in this?
I'm talking about what we did earlier. If you want, you can do it. You say, okay, I have some M that I want the mass to behave like, and then you can derive the controller. You'll find actually I need to compensate. First, I can maybe kill this mass and then compensate it with the new one. Or you can even add like some sort of force sensing, and then you can compensate it with that. So there's actually different ways to do it. Okay. Any other questions? Okay. So now this was the point mass part, and this was Q was in R3. So everything was, we did not need, everything was Euclidean, everything was nice. We were able actually to do this minus between psi and psi desired. We had the same case last time when we looked at the two-link manipulator. And actually, in general, this holds for any n-link manipulator, provided that the robot is planar. What does it mean that the robot is planar? In the end, the task space, or its workspace is just SE2. In the end effector, it will never go out of the plane, right? It always lives in the plane. You see this robot arm, for example, no matter what the angles are, it will always live in the plane. Okay? Even if it has 10 links. Okay? If they are the same, they're all, all of the joints, for example, are coplanar, then you may actually do this will make it always, the robot live in the plane. We call this a planar robot. Okay? We don't. Okay. Sorry? Definitely not. No. Because you can make the end effector go everywhere actually in space.
But we can make it act like a planar robot as well.
But you're going to be stopping some degrees of freedom. Yeah, of course. Yeah. For example, you can make it look it on the ground, and you can make it always move like this.
So any robot with a rotating base is not a planar robot.
Absolutely. Yeah. That's the easiest way to think about it. Yeah. Okay. So in this case, this is an example of a planar robot. And gravity can be anywhere, right? So gravity can be pointing down, but also if you can think of this robot actually as something from top down, right? So actually the robot itself can be moving, like that, and actually the gravity will be not affecting the robot at all, right? Because it's not in the direction of its motion. So for this case, we have SE2 to be our, our task space. But SE2 and H matrix in SE2 always has this form, right? It always has two numbers, psi x and psi y. And the rotation matrix part is isomorphic to one angle, exactly, to the phi angle. So in the end, we can simply say that Q also is theta, phi minus phi desired, psi x minus psi x desired, and psi y minus psi y desired. So the example I showed you last time of the two-link robot arm in the simulation was also very easy. It was also Euclidean impedance. Okay, we had simply R3. And the interaction wrench, because this is a planar case, we have only interaction tau, you have interaction torque at the end effector, something that's rotating like this, and you have force in the x and force in the y. Okay, of course, depending on which frame here, we're talking about the end effector frame. So this is the x and this is the y direction. Okay, And of course, you can transform everything with this joint if you want. So in the case we saw earlier, SE2 is simply just isomorphic to R3, okay? While the angle is simply, to be precise, the angle itself actually is from minus pi to pi, right? So it's like from minus pi to pi, and this is R2, okay, to be actually precise. But within that region, you just say, okay, it's everything is Euclidean, everything is R3. Yes. Okay. So if you're working with a planar robot, okay, you don't need any geometry. And as you said, okay, in general, of course not. So for a generic robot arm, okay, we have to be very careful. How do we define this error between the desired and the end effector frame? Okay, so this desired impedance now, this Q, I cannot simply say it's H minus H. Okay? It's not H of the end effector minus H of the desired frame. Okay? Of course, SE3 does not have vector space structure. Okay, so I cannot do this minus sign. And now, okay, the floor is open for any ideas. Okay, you'll find different ways to do that. Every way will have its own limitations. Okay, and it's even up until now, it's a matter of research. I was interested in actually this couple of actually this morning, and I just kept on looking for latest stuff here. Okay, and actually I found Neville Hogan as one of the students, okay, of Stefano Stramigioli. Remember the beginning of the course. So Stefano actually had one of the PhD students, visiting Neville Hogan at MIT during his PhD, and now they actually are still working on that. So the student is still working on this topic. So up until now, so even though it's this had been a lot of work in the 90s on the spatial impedance control, till now it's just people are still looking at it and very interesting. It's still exciting a lot of people because of all of the differences I'm going to show you in a bit now. Yes.
What kind of differences could we observe from different controller or different desired impedance?
I'm going to say it in a bit. Okay, just wait. Okay. And I'll show it even experimentally in a bit. Okay, what's the differences?
Why can't you take the error similar to the way we did it with the controller?
Very good point. Exactly. So this is not something new. We already looked at that exact same problem when we designed a controller for a PD controller, if you remember. We designed an energy balancing or a PD controller on SE3. We already talked about it. And we already looked at it that actually it's similar to SE3. That's exactly what we're going to be doing. Yeah, absolutely.
So why,
it's not something new, I know.
This is very complicated about the Q.
That's a good point because we have to wait. Okay, so I'll say it in a bit now. Okay, so now that's the motivation part. Now let's look at different ways. The easiest way that people think about is that they say, okay, you know what? I have two frames. Let's treat rotation and translation separately. Yeah. And this is, even before you taking the course, this would have been, the most straightforward way, right? Rotation and translation, they're not related, right? And now I hope you're convinced by now that okay, they are. So let's say, okay, my Q is simply an error in rotation and an error in translation. Error in translation is the easiest thing. It's just relative displacement, psi minus psi desired. It's an R3. We don't need to worry about it. And error in rotation, now you have a lot of ideas. Easiest thing, which is also before taking that course, would have been Euler angles, right? Let's say that I have Euler angles for the end effector frame, 3 angles. Euler angles for the desired frame. Let's take the difference between them. Right? This is an R3, this is an R3, this becomes an R3, everything is nice. An alternative is, let's do it a little bit geometrically, with something we've already talked about, which is the exponential coordinates. We said the exponential coordinates, they take you from small SO3 to big SO3, right? This is how we used it. And we used it, the Rodriguez formula. So the Rodriguez formula, you give it the n, if you remember the n tilde, and it will give you the rotation matrix, okay, with a theta. The log is the inverse of that map. So if I know that the relative orientation between the two frames is R desired transpose R, and I take the log, I'm going to get an error-like variable between the end effector frame and the desired frame. Of course, this is a log in SO3, so I'm only get the rotational part. And then the S inverse, what does the S inverse does? Converts it from a skew symmetric matrix to 3 numbers, to an R3 vector. And this is ER. Okay? It's another way. And the third way is exactly what you've already seen before. I don't need to remind you of it. Okay, we will study it inshallah, okay, in details. So it's given by this expression. How did we derive that? We said that let's look at this error variable as being the dual related to the co-differential of the potential function that was half trace of I minus R desired transpose R. Okay, so we got this from a potential function, okay, that took already that error. And that potential function we even didn't, play around with, this is why I'm saying this is, play around with it as you wish. Some people are, replacing this whole idea by maybe, for example, a neural network, by the potential function itself. You can actually have, let's try to have any function and learn, we know how to compute the derivative of it. So what is the best function for our task? You can do crazy stuff, but the same, math holds. So now there are different, you read this, if you just take this simple approach, okay, and let's start with the two extremes, this one and that one. So with the Euler-Angels approach, okay, this is actually what people were using for a long time before people actually started. This actually was, I think it was in the 90s. Yeah. So up until some people actually started to look at, this whole idea of the impedance behavior is not in, it's not Euclidean. There's actually some geometry there. And people started to look at the tools from differential geometry, and they came up with this idea of, they called it geometrically consistent springs, okay? Geometric consistency, okay? Or springs that respect the geometric nature of SE3, okay? Or in this case, just SO3. So, and then they started to play around with, so one of the main problems that they had when they were using Euler-Angels is that when I apply a rotation to the roll angle, when the robot wants to go back, it goes actually all of the three angles they get coupled. If you have a spring, okay, and you rotate one axis, what do you expect the behavior of the spring to be? Rotate back in what? Along the same axis, exactly. So that's the natural way of thinking of a spring, right? If you have three springs and they are at the same point, so I rotate this one like this, what is the behavior? It should go back like this. I rotate this one like that, it goes like that. I rotate this one like that, it goes like that. What happened here is that I rotate it like this, it does something like this. All three of them together, they change when they're going back. So the spring is like coupling all of them.
Is it because of the cross-coupling of the dynamics?
It's because SO3 is not R3. Put it this way.
Because also if we rotate, if three springs are connected together and if we give a twist to any one of them, some energy will be imparted to the others as well.
Even without talking about the energy itself, this is a control perspective,
And we saw that in the assignment as well for the Euler-Angel based.
Exactly.
We saw great
Yeah.
peaks for that. Yeah.
That's exactly what you've seen. So, okay, alhamdulillah. So now I know you did the assignment, not ChatGPT, okay? Okay. So now exactly if you did the assignment, you would have seen that already before, when you had the controller on SO3. And now I'm going to show it to you in a bit, actually, experimentally, okay? And that's the third one, which is the one that actually, the geometric one, that, we saw you suffered a lot for 3 lectures until, we derived it. But here, when you have this error, okay, it will behave properly. So I rotate an error like, along one axis, it goes back along the same axis, okay? So it's very natural. But it has a problem. And the problem, if you remember, was always at 180, right? The controller itself, when we derived it, it did not have one equilibrium point. The closed loop system was not only one equilibrium point. It actually had 4. Okay. Actually, it had even more. So it depends on how many 180 degrees. I don't know if you tried that or not in the assignment. But if you go back and you give your initial error to be 180 degrees away from where you want to go, you'll find that the controller will not move. It actually has 0 magnitude. The error is 0 if I'm rotated 180 degrees. So go back to the simulation and try it for yourself. It becomes even worse when we use exponential coordinates. Exponential coordinates, if you remember, we said that this was not a bijective map between SO3 and small SO3. It was not bijective, which means that not every rotation matrix will give me, an element there. Actually, at some points there is singularity. And the singularity is also at 180 degrees. So while this controller, the error will be 0, okay, at 180 degrees, this controller will have a singularity. It will even give you infinite number. Okay, so the torque will be infinite. Okay, so this actually will behave very badly. Yes.
For the inner angles, okay, I still don't get why there is cross coupling between the angles when you minus them, because for each one of them you're just taking the difference, hello, and this difference will create a torque, some torque from the actuator in this direction. So
That's right.
Why is there a cross coupling of it?
When that same torque gets applied on the robot, does it make the robot end effector move on a Euclidean space?
No, of course.
So that's the whole idea. Now, you can actually show it in math, and I'll give you some reading material if you want, some stuff that you can read on your own. There's a very nice chapter in the handbook of robotics on the force control, and they discuss exactly that point. They even derive it, and it's very, very easy. It's not really that hard. Very simple math. You can actually show that, and that's something very, very non-intuitive, that when we use Euler angles, the stiffness matrix, the true stiffness matrix that represents the spring on SE3, will become depending on the orientation that you're at. So when I change the orientation of what the robot is doing, and I do this whole idea of applying the error, I get different spring behavior. So the spring matrix depends on how you're moving. That's why it's coupling them. And that's why you need to look at a little bit of math there to actually to get convinced. And now let's go for the video. It's a very old video. It's from the 90s. Okay, but it's a very nice one. Okay, and this is part actually of the handbook of robotics. Okay. So I won't talk. Actually, it's self-explanatory until it finishes. But let's see why there is no voice.
The robot manipulator has 6 revolute joints. The experimental setup consists of a Comau Smart 3S industrial robot. The robot manipulator has 6 revolute joints with an aspherical wrist. The native controller is the C3G9000, a VME-based system.
This is the controller of the robot, okay? So you should be very fortunate that you're living in this age.
An open control architecture is available for this robot. Bus-to-bus communication links are established with a PC Pentium at 133 MHz, where control algorithms can be implemented as C modules. In order to carry out experiments of interaction control, an ATI 3100 force torque sensor is mounted at the tip of the robot manipulator via a suitable tool adapter. In the following experiments, different impedance control algorithms are tested at 1 millisecond sampling time. The feature of impedance control can be best understood if a surface is placed in such a way as to obstruct the commanded path. When the end effector tool comes in contact with the surface, a compliant motion is obtained so as to accommodate the interaction force and moment.
What actually happened in the last experiment is that they were commanding the robot to actually go first up until this point. So the desired part was inside of the surface.
Still the orientation
No, it was even with the same orientation, but you see everything, it was compliant in that direction, so nothing happened, It's like the surface is preventing it from having the orientation, so to have the orientation of what the surface is. That's the whole idea, right? It's being compliant to the environment.
When the end effector tool comes in contact with the surface, a compliant motion is obtained so as to accommodate the interaction force and moment. When performing a 6-degree of freedom interaction task, a spatial impedance has to be considered, involving an end effector position displacement as well as an end effector orientation displacement.
So now pay attention, okay? What you'll show right now is the Euler angle, okay, based impedance control, okay? And take a look at how the behavior of the end effector. So what he'll do is that he's going to rotate it by hand. So he's going to put an interaction torque around one axis and take a look at how the robot goes back when he removes his hand. Okay? Because when he removes his hand, it means that there is no interaction now.
According to the classical operational space approach, the orientation displacement is given by the difference between the actual and the desired set of Euler angles. When an external moment is applied about one of the tool axes, rotations are induced also about the other two axes. In order to overcome this drawback, a geometrically consistent approach can be pursued. The orientation displacement is extracted from the mutual rotation matrix between the actual and the decided and effective frame, either in terms of three Euler angles or in terms of a unit quaternion. Now, the rotation occurs about the same axis of the applied moment. A comparison between the two approaches under the same impedance parameters is carried out when the n effector comes in contact with the surface at a configuration close to a representation singularity. The recorded data confirm that the performance is much better with the geometrically consistent approach. Notice how the values of the contact force and moment on the bottom are smaller than those on the top with the operational space approach.
So this is the force, okay, that the robot is applying to the environment using the geometrically consistent, and the torque the robot is applying to the environment with the geometrically consistent, while this is the force and torque the robot is applying to the environment, but using the Euler angles approach.
Something that we also see in the assignment, the Euler angles usually produced much more torque, even though it returned almost the same speed.
Yeah.
Why? Still, it's not only it's rotating in the x and the y, but if we're only rotating around the z and the Euler angles are also rotating around the z-axis, it also produces much more torque.
That's the same. That's the whole idea.
But why? I don't see why.
That's up for you to play around with it. Okay, so that's the experiment. What you're saying is just matching with this plot.
Yes.
Why? Okay, so I promised at the beginning. So we're gonna have more questions than answers. Okay. Any more questions on this part? Okay. So what I just showed you right now is this idea of splitting actually rotation and translation, right? So here you think of that the spring force is K multiplied by Q, and Q is something that lives in R6, and this R6, variable is rotation and translation alone, and I can just now different ways of defining the error. But even this way is not actually a proper spring, okay? Because who said even that the spring force in SE3 should actually given by some gain K multiplied by the error? Where do you see this kind of error? Where do you see this kind of spring force?
Linear spring.
Only for linear springs, exactly. Only if you have a Euclidean spring. That you have K multiplied by delta X, right? K delta X, this is the spring elongation, right? And then K is just the stiffness. Springs, even in SE3 proper springs, so if you want actually to properly see it, you actually need to do it in an energy-based approach. And this is not something new, we've already done that. So if we say that I have a potential function on SE3 that characterizes the difference between these two together, so now the rotation and translation will be coupled, and the spring force will be defined in a way that respects the geometry. Even the stiffness itself will define the way in such that it respects that geometry. The spring force can be given by that expression, okay? The differential of the potential function, and you take the differential and you make it into an SE3 element, and that SE3 element you just make it into 6 numbers. So all of this term just becomes spring force, a potential force, okay, potential wrench due to the spring. While all of this term is simply damping, this is simply linear damping, and this is a linear inertia. So this we can do it like that. Even the damping itself, if you want to make it nonlinear, you can do it in the same way. You can define something called the Rayleigh dissipation function. You can take the differential of that function, and you can convert it to a damping, okay, a damping wrench. And we've seen, okay, this is an old slide from the paper when we talked about tracking on SE3, okay, by Bullo and Murray, and we said, okay, there are different potential functions that you can use, and actually you can play around with this, different functions, and you can, okay, and see what the behavior is. And as I mentioned earlier, the paper I just mentioned actually was 2025 in the International Journal of Robotics Research, and they were still up until last year, November last year, which is almost this year, okay, as a paper that people are still playing around with this stuff, okay, experimenting how does it affect impedance behavior and so on and so forth, okay. So I'll show you some experimental results. So impedance control is not just for manipulators; it's also even for drones. So here you're going to see this is one of the drones. Okay, this is actually one of my PhD work, and the guys here in in the lab are creating a similar drone to this one. They're almost done. Okay, so maybe inshallah we'll share with you the videos later. But we're trying to do something very similar. This is. Do you think with drones it's easier or harder than manipulators?
Easier.
This is the fully activated drone that you have. Okay, that you're using if you have it in your project, and it's actually much easier than the whole manipulator. The idea is very simple because when we had in the manipulator a joint space and a task space, okay, and the Jacobian was transforming between them, if you have one robot or one body, which is the whole drone, what this becomes? The task space is the configuration space, right? So it's like it lives in the sense, it doesn't have something called a joint space because there are no joints, there are no moving parts. It's just the whole body, it's one whole body. Actually, we call this actually a flying end effector. It's just an end effector that's flying without any, other bodies that are controlling it. And the propellers, we have 6 propellers here, so the 6 propellers produce a wrench. And you remember I told you earlier about that actually we're going to be designing a controller for this, assuming that we can control the wrench, and then we see what is the desired wrench, and we solve the control allocation problem and tell every individual actuator what the value it should have. So in the end, it becomes much easier. Yes, Magdalena. What do you mean by an end effector attached to it?
Like, let's say, for example, the carrying problem. Let's say 2 hexagonal
Okay.
carries in the box. That end effector, will it be considered as 2 joints, like the hexagonal itself and end effector, or will the entire thing be considered as one?
So this is actually the same drone you're talking about?
Yes.
It already has this long arm. Is there any moving parts here?
No.
So the end effector, the last point on the tip of the robot, is it moving with respect to the drone's body?
I mean, if the drone moves, it moves also.
Are you sure? So fix your arm and move your arm.
Okay.
Is my fingertip moving with respect to my arm? No. So it's the same motion, same twist. So in the end, if I control the body, I control the end effector. The whole idea, this is very correct, because when we did it in this paper, you can take a look at it there, we actually attached the spring. We said there's a virtual spring, right? That's connecting the desired and the end effector frame. We don't attach the spring to the body of the drone, the body frame, we attach it to the end effector frame. And now we're going to be moving it around, and it's going to be pushing and pulling, with the end effector.
When you're talking about impedance control with the drone, especially in this one, if you think about it, if you have any disturbances from the environment, the controller will not work for the body itself.
Okay, so
probably your impedance control is not on the drone itself. The drone itself will have stabilization control.
okay,
Impedance should be just on the hand. But
okay.
if you have now what are the different? How does the end effector? How will you satisfy the stabilization and also have impedance?
That's an excellent point. Okay, I'll first answer the first part that you said. Okay, if there are any disturbances, it will not work. Okay, I'll prove you wrong in a bit in 1 second. Okay, so I'll show you an experiment now, where the drone is. So now the drone is during interaction. So to actually fly it, you take it from the ground up. Okay, and then you have a desired end effector frame. Okay, so the desired end effector frame is here. The arm becomes pointing like that, and then you take the frame and you put it behind the wall. Okay, so the drone wants to go there, but it cannot because of the wall. So what does it do? Push on the wall. Okay, the pushing. So behind this wall, behind this part, there's a force and torque sensor. We put it there, and we're measuring here the force it's applying. Okay, so you see it already got in contact. Okay, so earlier it was we're measuring 2, so it was already pushing, and then we're taking the virtual desired point more inside of the wall. Okay, we're just pulling it. We're pulling the spring more and more and more. So it's applying more force. Okay, what you're going to be seeing down here are the individual PWMs for the rotors. The PWMs of this robot, they are all. They are thrust. These are propellers that can rotate only in one direction, which means that they can produce thrust only in one direction. Okay? They cannot produce negative thrust. From the way of the configuration of these propellers, when we ask it to push more, at some point, 2 of the propellers will actually reach 0. Okay, and they will want to shift to the other side, so that they can, start applying more force. But because they cannot, okay, we're just going to saturate the values. Exactly, we're going to cap the values to be 0. Is this a source of disturbance or not for the system? This is a very big source, okay? Because when you saturate the inputs, now you can try, go to your favorite controller if you have something there, try to saturate, the input, and take that input and give it to the system. You're going to immediately introduce, disturbances, and the whole system can be unstable. This is a very, very strong source of disturbances. Now let's see what happens. Okay. I don't think I have any voice. Yeah, I'm going to increase the voice, but it's just going to be, a drone screaming, okay? And I even muted it. Okay, so anyhow. So take a look at what's being written down. So it's applying the force. We keep on increasing this normal force until it reaches 10 newtons. Okay. Oops, sorry. Take a look at what happens when it reaches this point, at around 200 seconds. Take a look at this part. This propeller, what happens to it? It's not just stopping. Okay? It's like it's shattering, from 0 to something, 0 to something. And there's a dead zone. These robot, so these propellers, they have a dead zone. It's not like that I can continuously control them from 1,000 RPM up until 0. At some point, for example, from 200 or 300 up until 0, it's all 0. It needs to have, a little bit of high part. Even this dead zone is another source of disturbances. What about the performance? It's actually during interaction. So it's still applying the force, and at the same time, you've reached the limits, and what's happening? Nothing. So stability-wise, it's very strong. And the reason behind it is that actually this controller is something I mentioned earlier, and we never looked at it in details, something called passivity. This controller is proven to actually be passive with respect to the environment. And this includes also passivity with respect to unmodeled disturbances. Okay? This is not the impedance controller where we cancel things out. This is just the impedance controller where we have gravity compensation and the spring and the damper. Okay? So this is a very, very robust controller because we're not taking the dynamics and we're killing it. Okay? We're just keeping it as is, and we're just modifying the impedance in this way. And this you can actually show this, it's much better performance-wise, and this is just the proof. We repeated the same experiment. Okay, so if you want, you can take a look at the paper and the results there. We took this drone and we commanded it to have an angle, and you increase the angle, you increase the angle, you increase the angle. You get the same behavior, by the way, that actually at some point the propellers want to be negative, but you have to cap them. What happens when you reach that state?
And these propellers will be at maximum.
One propeller will be 0. It's not necessarily that the other propellers are maximum, but at least this propeller will be 0. So you're going to see that the drone is flying with 5 propellers, tilted like this, and it's working. If you don't believe me, I have a video I can show you. Okay.
This is singularity because one of the propellers stopped.
It's not singularity. It's just you've reached the actuator limits. The actuator has reached the limits, but the controller doesn't care because it's very, stable.
Still work.
Okay, to that work. Exactly, the controller still works.
It reaches a point where it tilts and
Then it's false.
It falls.
That will automatically. It's like you flipping yourself up, and you expect that and you have you're overweight. Okay, so you'll definitely not be able to fill it. This is the physical limits. You've just hit the physical limits of the drone itself. Okay, so one last discussion is about admittance control. Okay, because it's tightly related to impedance control, and I just wanted to get to know it. Okay. The idea of admittance control is exactly the opposite of impedance control. Okay? It's not clear at first. Okay? You really need to look at the math, and even when you look at the equations, you'll find that they're very similar, and you need to get your head around. But when you see impedance control or admittance control at work, you immediately identify this is impedance and this is admittance. Okay? But at least from the mathematical side, they're a little bit tricky unless you look at it in details. The most direct thing that the first difference between both is that admittance control requires force and torque sensing, either with an external sensor at the end effector or with estimation methods. You can have an observer and you can try to guess what the forces are at the interaction range. And the whole idea is that, you remember what's the difference technically between impedance and admittance in general? Mechanical impedance and mechanical admittance? But what was an input, what was an output? Force and motion, exactly. Does anyone remember what was input and what was output for impedance?
Impedance, it was force is the input and output is the motion.
The other way around. Right? So for impedance, you have motion as an input and wrench as an output. Motion as an input and wrench as an output.
It means that we want to achieve a motion.
No, it means that you're measuring from the robot its motion and you're outputting the forces it should, it should have. In this way, it's the opposite. Forces or wrenches are the input and motion is the output. And that's exactly what you see here. So the easiest form of an impedance controller, of an admittance controller, is that you're going to be measuring the wrench at the end effector using some way. You say, I want to have a desired spring and desired damping, and this is the desired impedance, the desired inertia. And what is changing here is the desired end effector acceleration. The desired end effector acceleration, yes, exactly. And of course, written like this way, I'm not discussing anything about the Q and the geometric consistent, all of that stuff, This is just the simplest case, assuming everything is Euclidean. And you can see how you can generalize this later. Okay? So the whole idea is that, you see, what is the input here is the force, okay, or the wrench, and the output is the acceleration. Of course, you can integrate the acceleration, you get Q dot desired, and you integrate it once more, you get Q desired. And Q desired, Q dot desired, and Q double dot desired is what you give to another controller. Exactly, there's even another control loop that's implementing this. Right? So usually admittance control is always put like an outer loop to another inner loop. And what you do with that is simply the following. Now take a look at the behavior between what admittance control can do.
This is impedance, right?
This is admittance.
Is that it?
What's the difference between this and impedance?
Isn't this similar to the one where impedance, but we call it dynamics?
No.
I think it's maintaining least resistance. No resistance is applied to the hand. And
Conserve the energy.
Kill
No.
the jerk, I think. Kill the jerk.
Okay.
I don't think it's feeling any resistance.
Okay. If I give you, this is the robot arm, and I have an impedance controller, and I push it.
They push back.
It pushes back, right? When I remove my head, what happens?
Come back to it.
There is a spring that brings it back, right? What is happening here?
It's staying in
Stay at the same, at the last position.
Exactly. It's like the desired frame itself is moving around. The desired frame itself is just moving around. You're calculating Q double dot, which means that it's changing. Q desired is changing. The desired frame is changing. Okay? And the robot is also following the behavior, okay, that you want in an impedance. You're designing that impedance. So it's like, this is, for example, a case where it's high damping. What does the high damping will mean for the user?
More resistance.
More resistance, exactly. So you see, you're changing how the robot will follow the hand of the user.
What about the spring? What will it appear? How will it appear?
Because if it's not just damping, there's also a spring, right?
How will it appear?
If you make the spring very high, it will follow and oscillate a lot. Okay? If you make the spring, for example, very compliant in some directions, it can follow, but at the same time it can be very wobbly. Okay? The thing about admittance control is that you can hardly see it. You have to feel it. The same also for impedance, by the way. You have to really feel it. You have to go to the lab, okay, and you can just play around with the actual robot and change the stiffnesses, and you'll see really what it means to actually have a virtual spring and a virtual damper, and the system really behaves differently.
For impedance control, I think it's very safe to work around the robot arm that has impedance control because it's compliant and you can push it. It's going to push back, but it wouldn't be hard enough. What about admittance here? How is it used?
Safety is a completely different story. Okay? Completely different story. So one of the top people in the field, Sami Haddadin, so the co-founder of Franca, what he actually did in his PhD 2009, 2010, after even some people did, but he took it really further before even making the company, Franca, was actually do a lot of stuff on safety. He has some crazy experiments actually where he put a knife on the robot and actually showed that it's actually safe, and he bumped it himself. Okay, so the videos are online. Okay, I can share them with you. Okay, but this is safety. And his group are still, up until this year, one of his PhD students is still working on the same problem, trying actually to look at safety. Because safety is not just about, that the robot is, safety is completely different from stability. When we're working with, with math, and you're doing stability analysis, you want to prove everything is stable, right? Stable, asymptotically stable, global asymptotically stable, all of that stuff. But when you have a robot and there's a human, what is safety?
Not applying too much force, not moving.
Not killing the thing, not killing the human, right? Or breaking his arm, making an injury. Exactly. There's more stuff to it. And this is what safety means in that respect. Okay? And being stable doesn't mean you're safe. It's completely different things. Okay?
So in general, this admittance is applied in the teaching mode of the R.
I cannot say 100% yes because I haven't seen how they do it, but I guess 100%, 75% yes. Yeah, that's exactly what they do. When you press on it, okay, you go into teaching mode. So teaching mode, okay, it's telling it I'm gonna be applying a force. It has a force and torque sensor at the wrist. Okay. Not only that, the Franca, for example, in particular, it has a joint sensor at every joint. Okay, sorry, it has a torque sensor at every joint, in addition to a force and torque sensor at the end effector. Okay, the force torque sensor is 10,000 reals plus. Okay, okay, and, this is a very cheap one. Okay, okay, so the force and torque sensor is is at the end effector, and what teaching mode actually does is that you apply here at when you're holding it, so you're applying the wrench at the end effector, okay, and then you start to move it around, and it just stops there. Which behavior does it follow? Is the behavior that actually was programmed. Now, for example, the Franca, it has the API that allows you to actually implement your own controllers, and you can try to actually change this. You can actually go for the teaching mode, but you can make the behavior completely different. You can make it very, very light, very, very stiff, very, very high resistance, low resistance, and so on. You can feel different things. Which brings us to the last part about, okay, doing it actually with drones. Same idea with drones. Okay, so this is the group of Raffaello D'Andrea. Okay, again, one of the top, okay, in the field. And this is one of his TED Talks that actually he does admittance control for a quadrotor. They don't have a force and torque sensor on the quadrotor, so the way they do it actually is that they estimate the force using some Kalman filtering and stuff like that. Okay, so that's another way of how you can do it. This is actually a very nice video. Okay, and that's the last video of the course. Okay.
Interaction doesn't have to be virtual, it can be physical. Take this quad, for example. It's trying to stay at a fixed point in space. If I try to move it out of the way, it fights me.
This is impedance.
It moves back to where it wants to be. We can change this behavior, however. We can use mathematical models to estimate the force that I'm applying to the quad. Once we know this force, we can also change the laws of physics, as far as the quad is concerned, of course. Here the quad is behaving as if it were in a viscous fluid. We now have an intimate way of interacting with a machine. I will use this new capability to position this camera-carrying quad to the appropriate location for filming the remainder of this demonstration. So we can physically interact with these quads, and we can change the laws of physics. Let's have a little bit of fun with this. For what you will see next, these quads will initially behave as if they were on Pluto. As time goes on, gravity will be increased until we're all back on planet Earth. But I assure you we won't get there. Okay, here goes.
Okay. And with that, so that's the end of the course. Okay. Thank you very much. Okay. So I hope you enjoyed it. Okay. So we've started from the math. Okay. We ended with the robotics. Okay. So I did not lie to you. Okay. When I told you, okay, this was a math course, and I did not also lie when I said this is a robotics course. Okay. Okay. جزاكم الله خير. السلام عليكم ورحمة الله وبركاته.